Everyone knows that the lateral surface of a right circular cylinder of radius r and height h can be expanded to a rectangle, and thus computed in an instant to be 2 pi times r times h. But what if I tell you that calculus can fail to compute this result when the standard ideas are applied? Yes, calculus will give a result which is different. Stay with me to see the calculation and then understand what has gone wrong with calculus. Calculus is an extraordinary tool. It makes an average person to be a superior mathematician than those mathematicians who lived before Newton and Leibniz. Around the age of 12, Galileo, with only the tools of theoretical Euclidean geometry, computed the centroid of a truncated cone. Upon seeing the calculation, the Pope declared the kid a genius destined to become a famous mathematician. Today, the centroid of a truncated cone is a routine calculation in any introductory freshman physics course. If a student does perform the calculation, the instructor places it on record as part of the required work. If the student cannot perform it, the instructor flags the student as weak. So great is the power of calculus. Over the few centuries that passed since its discovery, calculus has been polished by the work of thousands of mathematicians, and it has become easy to learn. Calculations are straightforward. However, often small conceptual details are missed, and then erroneous results are obtained from the calculations. We are about to experience how easy it is to miss the guiding concept in a calculation. Let's start with the calculation of length to remind ourselves the basics. Everyone knows Archimedes' method to compute the circumference of a circle. We inscribe an initial polygon to the circle. Say that this polygon is a square, which is very easy to draw. The sum of the sides of the square approximates the length of the circumference. But this is a very rough approximation. By dividing the 4 arcs in halves, an octagon can be inscribed. The sum of the sides of the octagon approximates the length of the circumference better, but it is still a rough approximation. However, we can repeat this doubling process ad infinitum. We can draw a hexadecagon, a triiconodigon, and so on. The approximation gets better and better, and, in the limit, the sum exactly gives the circumference. The calculation is easy. Let the polygon have n sides. Using the altitude of a triangle formed by the center of the circle and 2 successive vertices of the polygon, the side of the polygon is computed easily from the radius of the circle. The perimeter of the polygon is then n times the length of one side, and, in the limit n to infinity, the perimeter of the polygon coincides with the circumference of the circle. Recalling the well-known result that the limit of the sine function of x over x as x approaches 0 is 1, we recover that the circumference of the circle is 2 pi r. In general, a curve AB can be approximated as a polygonal line from A to B with vertices on the curve AB. Each segment of the polygonal line is a chord of the original curve. Thus, the length of the curve AB can be approximated as a sum of the lengths of the segments that make the polygonal line. In the limit that the number of vertices of the polygonal line goes to infinity and the length of the segments goes to 0, the length of the polygonal line equals the length of the curve AB. I will use now this simple and straightforward idea to compute the lateral area of the cylinder. More precisely, I will inscribe a polyhedron, and then I will take the limit as the number of faces of the polyhedron goes to infinity and their area to 0. Towards this goal, let's divide the cylinder into m smaller cylinders of height h over m. In this way, the original cylinder looks like a roll of coins. Starting counting at the very top of the original cylinder, there are m plus 1 bases. We divide each circumference of these bases into n equal parts by selecting n equidistant points, such that the selection of the points obeys the following rule. For all odd bases, first, third, fifth, etc., we choose the division points on the same vertical lines. Then, consider the midpoints of the arcs determined by the division points. For all even bases, second, fourth, sixth, etc., we choose the division points on the same vertical lines as the previous midpoints. Having all partition points, we take any 2 neighboring points on a base circumference and the point above their midpoint on the adjacent upper base circumference, and we form a triangle. We also create a second triangle by connecting the same two neighboring points and the point below their midpoint on the adjacent lower base circumference. After we have formed all possible triangles, we end up with an accordion-like polyhedron inscribed to the lateral surface of the cylinder. Using simple algebra like the one shown in the calculation of the regular polygons in the approximation of a circle, we can compute the base and altitude of each triangular face of the inscribed polyhedron and from them the area of each face. The actual calculation is not important. If you want to verify it, pause the video and work it out on your own. Now, the polyhedron has two MN faces. Hence, the approximate area of the lateral surface of the cylinder, which equals the surface area of the polyhedron, is easily found. It's shown inside the box on the screen. I have reorganized the formula in a way that is more convenient for taking the limit as we increase N and M without bound. Notice the appearance of sine x over x, which goes to 1 as x approaches 0. Then, under the square root, notice the ratio of m over n squared. The limit of the formula depends on the limit of this ratio. Say that this limit is L. Then, the lateral area of the cylinder is found to have a value different from the standard value. In fact, the formula predicts a different area for each value of L. Only for L equal to 0, which happens, for example, if n is equal to m, we recover the well-known formula for the area. How is this possible? If you want to think about the paradox that we just uncovered, pause the video and try to find a resolution. Once you have decided that you know the answer, continue the video to compare it with mine. Are you ready? Let's check if you got the resolution right. The previous paradox was discovered by the German mathematician Hermann Amandus Schwarz in the 19th century. To mathematicians, Schwarz is widely known for his work on complex analysis. To students, he is known for the Cauchy-Schwarz inequality, which appears in arithmetic, geometric, function-theoretic mathematical problems in physics. Schwarz's paradox is not a paradox at all. It only demonstrates that defining the area of a surface as the limit of the area of the inscribed polygons hides an important conceptual complication that is not evident without deeper investigation. The polyhedron that has been constructed serves as the instrument to reveal this complication. Once more, let's review the procedures of measuring lengths and areas. To define the length of a curved line, it must be divided into small pieces. Then, the length of each piece is measured by projecting it to the corresponding tangent line of the curve. Similarly, to define the area of a curved surface, it must be divided into small pieces. Then, the area of each piece is measured by projecting it to the corresponding tangent plane of the surface. The key words in the definitions are tangent line and tangent plane. The two procedures appear identical. However, by simply drawing polyhedrons in the two-dimensional case, more than often, we break the requirement that the calculation uses the tangent planes of the surface. In the one-dimensional case, when the partition of the curve is fine enough, the direction of the chord joining two neighboring points of the partition approximates the direction of the tangent line at any point of the corresponding arc. Hence, no mistake can occur, and no special attention must be given how the partition is chosen. However, this is not the case in 2 dimensions or more. A polyhedron can have all its vertices on the surface while at the same time, each face can form a large angle with the corresponding tangent plane. Such a polyhedron is not a good approximation of the surface and must be excluded. This is exactly what happens with Schwarz's example when the limit L does not vanish. The larger this limit, the closer the faces of the polyhedron to being vertical relative to the tangent planes. By selecting the faces this way, the total area of its faces can become as large as we wish. You now understand that, although ideas in calculus are simple, sometimes their execution requires extra care to avoid mistakes. With experience, this becomes instinctual. I hope you liked this video. If you did, please subscribe to my channel to help the creation of more videos. Thanks a lot for your support.